Okay, hi everybody. Happy Friday. So this is a video lecture that I recorded for you to watch and to go through what we're about to learn today, which is about how to solve circuits that are in a series and in parallel. But a few housekeeping things just to kind of review what's going on in class right now. So on Thursday, you finished up your Ohm's Law lab and the practice problems that are associated with that. Today you're watching a video and you'll have some book homework to work on after you guys watch this together. Monday, you're going to come in and you're going to work on this series and parallel circuits packet, which is practice problems of what I'm about to review with you today. And I'll make sure that there's a key posted to that on Schoology. And then make sure on Monday night, or at least over the weekend or something like that, you watch the video about your PhET lab that's posted on Schoology for Tuesday so that you're prepped to go through this PhET lab together come Tuesday, and then you don't have to watch the video in class because that's more boring. Okay, so for today, we are going to be learning about resistors that are in series or in parallel. So if you could take out this marigold note taker that's in your packet for me, please, and thank you. Okay. So we have this from our PowerPoint. Okay, perfect. So as we're just kind of walking through this, we've been talking about circuits. We've become really great experts on Ohm's law. So voltage is equivalent to a current multiplied by a resistance. Now today we're going to up level our circuits a little bit more by adding more resistors. So more than just one that will be within the circuit. But just a little bit of review about how circuits are structured. So there's kind of two different main ways that you can see a circuit. The one that we're dealing with almost 100% of the time is a closed circuit. So a circuit that has a complete path for all of the electrons to follow. There's no break in the circuit. The electrons always go across the battery, through all the resistors, and back to the battery. So we call that a closed circuit because it's all encapsulated. If there is not a complete path, then the charge is not going to flow through the whole circuit, then there won't be any current. And so we actually call that an open circuit. And the way that open circuits are useful to us is we use them for switches. So if you think about a light switch, when you're turning the lights on, you're making the closed circuit. When you're turning the lights off, it's like you're making a break in the circuit so that the current can't flow anymore. So that's a switch, and that makes it an open circuit because there's an opening where the electrons can flow. Sometimes you might have also heard people say, my circuit, it's shorted out, or I have to go and flip my switch outside my house because I have a short circuit. So that is a circuit that doesn't contain a load. And what I mean by the vocabulary load is that it's what's allowing all of the voltage and the energy that's in the battery to be dissipated throughout the entire circuit. So a short circuit would be something that doesn't have a resistor. Like you connected a wire to another wire to the other end of a battery, and we didn't have any sort of resistance, anything to control the current. So these can actually be really dangerous because if you have a lot of current running through a wire, a lot of energy, that's going to release a lot of heat. And that's how electrical fires are started. So electrical engineers do their best to not short circuit any of their wires, that they always include resistors. But it's just something to know about where that vocabulary word comes from. Another little vocabulary review before we get to the math today is that you're going to see in some of your homework problems tonight them use the vocabulary term EMF. That just stands for electromotive force. This is another one of those lovely ways that physicists talk about potential difference. So remember, potential difference, it's the difference of voltage across some sort of power supply. So the most common example being a battery. So if in a problem they say the EMF of the circuit is 9 volts, you're just talking about what the voltage of the battery is. Any device that transforms non-electrical energy, so think of something like an electricity generator, so like a wind turbine that's then generating that into electrical energy. it's a source of EMF, of an electromotive force. Now, it's not actually a force, but we're just saying we're gathering electrons to make electricity through other sources and then putting that into electrical energy. So like a battery comes from chemical energy, a generator comes from mechanical energy. We're just talking about a transformation of energy that gives us our voltage. And last reminder here, if you're going to decrease voltage of circuit components, it's always going to be equal to any sort of increase in the voltage across your potential difference or your power supply. So all of this follows the law of conservation of energy. Energy in equals energy out. Okay, so that's the vocabulary for you, just kind of that first top section on your note taker, just a little review of some words. So we're going to get into the mechanics and some of the math of this today. So far we've been dealing with circuits that have a battery and have one resistor. Today we're going to add more resistors to our circuit. And we're going to add them in two different categories. So the first category is called resistors in series. So this describes a circuit that has two or more resistors or two or more components in the circuit, and it's just providing a single path for the current. So you're going to have one resistor after the other. So this is kind of like some of the examples we saw in the very first day when we learned about circuit schematics. You drew your battery and then you drew another resistor on one side, another one, and another. They just keep going and going and going. So you can have as many resistors as you want in the circuit, but they're going to be lined up on the same pathway, one after another. So an example of what that looks like is in this picture right here, or which is representative of these lights. So a battery that's connected to a light bulb that along the same wire is connected to another light bulb. You draw this in the schematic like this. So the battery you have, if you run this way, the first resistor is connected now in series with the second resistor. So they're along the same line. So some of the rules about how we now apply Ohm's law, or we want to solve for the voltage, the current, and the resistance across the entire circuit, is we're going to manipulate these rules of Ohm's law a little bit to fit resistors that are specifically in series. So resistors in series carry the same current throughout the entire circuit. The current across the battery is the same as the current across this resistor number 1, which is the same as the current across resistor number 2. So this is because charge is conserved. So charge is not going to be able to build up or dissipate from point A to point B. The charge in equals the charge out, which means the current in equals the current out. So that's rule number 1. The current is always the same throughout, no matter where you're at in the circuit, if it's in series. Okay, new vocabulary term for you, something that's called the equivalent resistance. So now we're dealing with more than one resistance. We're dealing with, in this example, you have 2 right here. The equivalent resistance describes the sum of all of the circuit's resistances. So that would be if you wanted to describe what is the resistance for the entire circuit. Well, that would be the equivalent resistance. If you were describing the resistance just at resistor 1, then you call that resistor 1 or R1. So the way that you calculate the equivalent resistance for a circuit that's in series is you add them all together. It's all additive. It's just the sum of all the resistances. So the equivalent resistance is equivalent to the resistance of the resistor number 1 plus resistor number 2 plus resistor number 3, and so on for as many resistors as you have. So how do we then apply Ohm's law to this? So 2 or more resistors in an actual circuit have the same effect on the current as one equivalent resistor. That's a big concept right there. So what we're saying is that the equivalent resistance, the sum of the resistors, is going to act the same for the actual circuit and the current that runs across it everywhere. So this is actually why current is the same everywhere, because current is only relatable to the potential difference and the equivalent resistance. So if we apply Ohm's law, which tells us voltage equals current times resistance, and we rearrange that to solve for current, so current equals voltage divided by resistance, We can then find what is that total current in the series circuit. So it's just going to be equal to the potential difference of the circuit, whatever power supply voltage you've been given for your circuit, divided by the equivalent resistance. So the sum of all the resistances. So that's going to tell you what your current is. And remember, the current's going to be the same everywhere in a series circuit. So this picture really describes this well. It's like if you combined both of these resistors together and you just found the sum, it's one sum, one equivalent resistance, which will help you find what the current is everywhere in the circuit. So this is the big idea of series circuits, and it's really this table that helped me solve circuit problems. So there's a place for you. It says the big idea of series circuits for you to write this down. So the first thing that we kind of just to summarize and add into this is that the voltage, the total voltage of the entire circuit when it's in series is going to be equivalent to the potential difference across the first resistor plus the potential difference across the second resistor plus the potential difference across the third resistor and so on. So V total is equal to V1 plus V2 plus V3. So voltage is additive. You can now, and we're going to do this with just similar to how we did our Ohm's law, when we start to connect resistors in series on our circuit kits and you actually look for what that is, the potential difference is going to be different across each resistor when it's in series. But the voltage of across resistor 1, 2, and 3 equals the total voltage across the battery. So it's additive in that sense. And that's a really great property to know because you can always check your problems to make sure you're right. If your voltages aren't adding up, then you messed up somewhere along the way. So the second thing that we learned is that current is the same everywhere. The total current is the same as the current across resistor 1, which is the same as current across resistor 2, which is the same as current across resistor 3. All right, the third thing we learned about is a new vocabulary word. What is an equivalent resistance? Well, it's just the total resistance across the entire circuit, and we also learned that this is additive. So it's going to be the resistance of the first resistor plus the second plus the third. So what is a real life example of what something like this looks like? It's kind of like your Christmas lights. So if you had a bunch of light bulbs connected in series, the filament that runs across a light bulb is just like a resistor. It helps control the current. So when things are connected in series, if you have one bulb that goes out, the whole string of lights is going to go out. That would create an open circuit where electrons can no longer flow through. So this is useful in some areas, not so useful in others. And we'll, as we talk about more complex circuits upon my return, we'll talk about kind of the purpose of electrically lining things up in this way versus the other. Okay, so that was circuits in a series. So let's do a little sample problem for how we would mathematically utilize this information to solve for the different components of a circuit. So this has a 9-volt battery is connected to 4 light bulbs as shown in this picture. So we want to find the equivalent resistance for the circuit and the current in the circuit. So what we are given is, from this picture, we're given the voltage of the battery, the resistance across each light bulb. Now I just labeled them in the order that I saw them. So I said this is 1, this one's 2, this is 3, and this one's 4. Okay, disclaimer. We're really more like pay attention and do this every time. Every single time you solve a circuit problem, you must draw a circuit diagram. You must draw the battery and you must draw all of the resistors. Now remember our rules, it's always a rectangle. You're going to spread out the resistors as much as you can. Just make sure that you can distinguish between each resistor. So we have 4 resistors here. I have the diagram shown right here that you can draw to the side. And so this is kind of going to be one of our rules falling forward. Every single time you face one of these problems, if a diagram is not supplied to you, you are going to draw the diagram. That's a great way for you to write down your known values in a way that's really easy for you to see. So then the rest of this problem, we are asked in what is unknown. What are we looking for is the equivalent resistance and the current. So I'm going to just like count to 15 in my head and just give you a second to write this down. Okay, if there's any major exception, like pause it if you need to. Okay, so continuing on with this, how the first part asks us to find the total resistance or the equivalent resistance. So remember, equivalent resistance is going to be the resistance in 1 plus the resistance in 2 plus the resistance in 3. So if we were to add all of these together, we would do 2 plus 4 plus 5 plus 7, which would tell us that our equivalent resistance is 18 ohms. Okay, 18 ohms right there. It's like really white on this picture. I don't know why it didn't show up super well. But 18 ohms for you. Okay, so then if we're solving for our current, we're just going to use plain old Ohm's law. So maybe I will switch this so I can kind of write this on the board and maybe you can kind of see as we're going through this. But for when we're solving Ohm's law, we say that a current is equivalent to our voltage, which is going to be our total voltage, divided by our equivalent resistance, which I just write Req. So if we're solving that for this problem, our total current that's running through is what we're solving for. Sorry, I was just looking at my screen. So actually our total voltage is just what's running across the battery, which is 9 volts. We just determined our equivalent resistance to be 18 ohms. And then if we take 9 divided by 18, that's going to give us 0.50 amps as our total current for the problem. So that gives you an example of how you're going to solve the different components of a series in one of these. So then if you flip to the back side, if we start to look at parallel circuits differ from circuits in series because they offer multiple pathways for the charges to complete the circuit. So you can kind of see from the picture, if you were to have an electron travel, and it would have a crossing point right here. It could either come across resistor 2 or it could come up and come across resistor 1 and come back to the battery. So that's the multiple pathways. You always draw these kind of like a rung ladder where one resistor is on each rung of the ladder as you're drawing them. So some kind of rules that parallel circuits very much so differ in the rules from series circuits. So you don't want to mix up these rules, which is why we're going to kind of make some tables to help us remind us of all this. So one, the resistors get the same voltage. You're looking at the same potential difference across R2 versus across R1s because they're connected to common points on the battery. The resistors can very much so have unique currents. So current is not the same throughout the entire circuit in a parallel circuit. That's because we're running along these different pathways with very unique resistances. But the overall resistance is going to drop as you add more wires in parallel. Now, I'll show you more what that means when you see this mathematical relationship. Oh no, this looks like so bad. Let's see if I can get this to look at something else. I'm having a hard time getting this to show up. Let's see if I can open this up on a different tab so you can see it. Pause, please. Thank you. All right, let's try to share. this tab instead. And let's come down. Oh, no, we already learned about that. Oop, that's your homework. Okay, we're finding it. Okay, this looks much, much better. Okay, so our big idea for resistors that are in parallel is going to be one of those things that I talked about, that voltage is going to be the same throughout. Oh no. I don't know why this part didn't show up. I'm just going to type it in real quick. Our total, oops. My bad. Okay, let's add. I'm like makeshifting this as it's going because it wouldn't let me share my other screen. Okay, here's the dandy old equation that you need for this part. Okay, so big picture, your voltage across every single resistor is going to be the same when they're in parallel. Your current is going to be additive. So the total current for the entire circuit is going to be equal to the current that's running across resistor 1 plus the current that's running across resistor 2 plus the current that's running across resistor 3. Okay, the screenshot that I just added here that's fancy dancy. This is how you calculate the equivalent resistance. So it's an reciprocal relationship. So it says that 1 over the equivalent resistance equals, well, it's really, we're just saying 1 over the total resistance equals 1 over the resistance for R1 plus 1 over the resistance for R2 plus 1 over the resistance for R3, and so on. So when we're talking about that reciprocal relationship, your equivalent resistance is always going to be less than the smallest resistor in the group. It's because you're doing this inverse relationship, this 1 over. The reason that we use resistors in parallel is because, unlike our last example, if one light burns out, the others are still going to turn on because there's that alternative pathway for charges to follow. So this is like what a light bulb would look like if it was in parallel. You have all the light bulbs, more than one pathway for the electrons to travel. Okay, so a little bit of calculator simplification for you for your equation. This 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. Kind of just want to show you in your calculator real quick that instead of doing 1 divided by when you're doing this, there is a lovely inverse button. For my calculator, it is this x to the -1 button right underneath the math button. And if you use that in your calculator and you set it up like I have here on the screen, and you say, doing this inverse 1 is like saying 1 divided by. So if you do R1 to the inverse button plus R2 inverse button plus R3 inverse button, and then inverse everything, that's a much easier way to plug this in your calculator, and I'll show you that when we do our example problem. Okay, so here is our sample problem. A 9-volt battery is connected to 4 resistors as shown in the right. Find the equivalent resistance for the circuit and the total current in the circuit. So what we're given is the potential difference. The resistor, I just named them. So R1 is 2 ohms, R2 is 4 ohms, R3 is 5 ohms, and R4 is 7 ohms. We're looking for the equivalent resistance and the current. And again, number 1 rule from now on, you are always, always, always going to draw a diagram for these problems. So again, these ones look like rungs of a ladder. The way that I took a screenshot of this, it kind of makes it look a little silly. The way I drew this on my paper, let me see if you can see this. I kind of draw them more so that they're like right on top of the other. You'll find your own style as you draw more of these, but you see I have the 2 ohm, then the 4 ohm, then the 5 ohm, then the 7 ohm, all on the rungs of my ladder, and then the battery being the bottom rung of my ladder. So it's totally up to you and how you like to draw them. Let me move this so to make sure you can see that. There's your drawing for yourself. And I'm just going to count to 10 in my head, give you one more second to finish drawing this, and then we'll move on. Okay, sorry, my graphics are not showing up super well, but for when we're calculating this, first thing we want to know to find is the equivalent resistance. So, sorry, this is like, when you're finding this, you're doing that 1 over method. And if you like doing the division by 1, you're more than welcome to, but your equivalent resistance is going to be, I think my 2 and my 4 got totally smashed, but it's going to be 1 over 2 ohms plus 1 over 4 ohms plus 1 over 5 ohms plus 1 over 7 ohms is going to be equal to 1 over your equivalent resistance. Okay, so let me show you how to plug this into your calculator using that +1 button. So I would do my parenthesis, and then I'm going to do 2 with my inverse button plus 4 with my inverse button plus 5 with my inverse button plus 7 with my inverse button. And then, so that's what you should have so far. I'm going to close my parenthesis and add 1 more inverse. And that is just a really simple way to write this into your calculator without having to do the 1 divided bys. And we click here, and it gives us the correct answer of 0.91, and it goes like 50, blah, 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 blah. But I think if you did it the old-fashioned way, you got a little different rounding, and it was 0.917, but you're about to the same way there. So that's a little trick for your calculator of how to do these. Okie dokie. So that's the equivalent resistance. Sorry, the image is not great. Doing my best here. Okay. The second part is to find the current near the battery. So we do Ohm's law. Voltage is current times resistance. Rearrange that to solve for current. Now you're going to say that it is your potential difference, which remember when they're in parallel, it's the same across everything. So for this, it's just 9 volts divided by your equivalent resistance is going to be, what we just found, 0.917 ohms. 9 divided by 0.917 gives you 9.8 amps for your current. Remember that current is not the same throughout every single resistor. So the one more part of this question asks, what's the current that's only running through resistor 1, the 2 ohm resistor? So you would just take the voltage of the battery, which is 9 volts, divided by that resistance, which is 2 ohms, to get the current that's just running through that singular resistor. Now, remember one of your rules is that the current total is equivalent to the current running through resistor 1 plus the current running through resistor 2 plus 3 and so on. So the sum of each individual current running through each resistor will add up to the total current. For this problem, the sum of all the individual currents would add up to 9.8 amps. So this is what we learned in review today, learning about circuits that are in series versus circuits that are in parallel. This is in your textbook, a really great summary of everything to look forward to. I will post this note taker on Schoology in case you kind of missed writing any of this down. Sorry, my graphics weren't super great. And so then you are going to work on your homework for the rest of class, which is, I changed slightly from your calculator, but it's page 650, numbers 2 through 5, and page 655, numbers 3 plus 4. So those are the practice problems that are in your book. So page 650, numbers 2 through 5, page 655, numbers 3 plus 4, and I will be making a homework help video that walks through those problems for anyone who would like to look at that. But other than that, just go work. Cool. Thank you. Bye.